company update.
Tinybox greens are pretty much in stock. We got another order. We sold one more Tinybox red, so there's actually only one Tinybox red left. And yeah, Tinybox greens are flowing now. I think I'll send out a marketing email this week and we'll see. Oh, also, AMD supposedly sent us a FedEx tracking number, but last time I checked it, it didn't work. Let me try it again.
Oh, that's for the machine.
Wait, what? I have a lot of questions about this. We got something else about the contract too. I have a lot of questions about it, but we'll see. Yeah, we have a FedEx tracking number. Doesn't even look like. Oh, wait, what? Delivered?
Oh, we got box.
No, this is something else.
Oh.
Who can use the internet's so hard to use?
You're in the tracking number.
No, the tracking number can't be found right now. So I don't know about that. No box.
Okay. Okay, great. Okay. Do you want to discuss your blog post?
Yeah, I mean, I think the main thing really to discuss is to realize that, like, MLIR is just the Waymo approach to neural networks. It's the same thing, right? It's this idea that, like, you're going to be able to build a framework that's flexible enough to capture everything, and then you'll just have the framework, and you'll have different people work on each part of the framework, and the different people, some people will work on cones, some people will work on speed limit signs. And then it'll all come together and create a great system that's going to outperform everything. And I just don't think this is true. I think it's the exact same thinking that leads to Waymo. MLIR has a Conv3D guy whose job it is to do Conv3Ds. Oh, and even worse, he's doing Conv3Ds and uint8 on AMD. Like, this just isn't going to work.
I mean, maybe not.
No, like it'll work.
I guess imagine how people would discover Winograd.
I mean, Winograd.
I think only because someone looked into COM that come out with Winograd that really only works for small COMs.
Winograd's a little bit different from what I'm talking about, right? Winograd actually changes the compute itself.
Yeah, that's what I mean.
Well, yeah, but I mean, we're always going to be able to express things like Winograd at a higher level. I'm talking about when you have the compute that's fixed, you need to determine how to properly schedule that compute. Right? You know the graph, and you're asking the question, how do I best schedule this graph across this hardware? Across these 20 GPUs, across... Yeah, so I think that, like, the bitter lesson has to win here. There's no
more. You like elaborate more for the sentence.
Well, there's no way that, like, as these systems continue to grow and get more complex, there's going to be more and more compute put into tuning, basically. Right, to put into, like, if you're about to run a huge training run, the only thing you care about is the overall cost of the run. So you want something that continues to scale with more input compute. You want something that continues to get faster. You're like, okay, well, I'm about to do a huge search to figure out how to make this thing as fast as possible.
Yeah, but what's happening to LLM is there's literally just 3 components to LLM training, and they just make it repeated multiple times.
Yeah, like
So I guess what you're saying is true is in the world that has a huge diversity, like huge diverse models that it's impossible to hand tune each of them like how we tune LLM now.
yeah, I mean, if it's true that the world is just literally only LLM, then this probably doesn't make much sense. But I mean, the world just like even today, we're already seeing what the successor to the transformer architecture is. It's diffusion. Like, there's going to be aspects of the transformer that continue over, but like, Comma has moved away from all our video gen models are diffusion. They're not transformers. And I don't think that this really stops. I don't think that there's going to be a massive collapse into a single model type.
Yeah, but let's say maybe it's not one, but let's say 10. Don't you think
I don't even
engineers collaboratively can optimize 10?
I don't even think it's going to be 10. I think that the reason you're getting this, the reason right now you're seeing so much stuff be shoehorned into a transformer, even when maybe it shouldn't, is because the minute you step away from the beaten path of transformers, everything becomes a lot harder to run. You now need you if you think about the engineering years that have gone into optimizing transformers, the minute you step away from that, you no longer have that. So even if your new architecture is better, it's unoptimized.
Yeah, but this is just, I mean, then will there be a time for it's too late? Like, say, if you want to start a brand new operating system because of a new design and new learning, and you find all the problems in Linux, and Linux is grow like this super big in terms of line counts and complexity.
Well,
So that also fits in that. But now, how does this new operating system with the new best principle going to win?
yeah, I mean, I think that Linux is. If I came up with a new like operating system, right, how do you compare and contrast that to Linux? Or how do I make an argument that my operating system is better?
You can pick certain hardwares and certain workload and say your operating systems perform these workloads better on these hardwares. Pretty
Uh,
much how we are doing now for Tinygrad compared to other stuff, right?
well, no, but it's different, right? Like most of the reason that somebody chooses an operating system does not come down to the performance of the operating system.
How so?
I think people choose an operating system a lot more for reasons like app interoperability, for example.
Okay, then why is that not the case for deep learning compilers?
Because the apps are so simple. Right? There's nothing in deep learning that today you can't respecify in a day. There's no model that's more complicated than what you could write in a day in Tinygrad and fully specify the model exactly. Whereas if you asked me to write Chrome, it's hopeless.
Okay, so because the app is very simple.
I think so, yeah. I think
Oh,
the app
so which pretty much translate to the switching cost is fairly low.
exactly, yeah. I think the switching cost from framework to well, there's
But
also like
is that true?
that the
Like,
switching cost is low.
yeah.
Well, I mean, neural network framework includes a lot of different things. And I think like in the future we'll have better words to talk about all of these, but eh, like switching from if I have something that's running an Onyx model, I'll switch in a minute. The cost of switching from like Onyx runtime to something else. Now, if I have a huge code base and an ecosystem in Torch, yeah, okay, that's a bit harder to switch. But again, okay, that's why it'd just be a backend to Torch. In the same way that like both BSD and Linux can run C code or can run Python. Like if I have a Python library, I can run it probably just as easily on Linux and BSD.
Okay.
Yeah, I think there's a like, I'm not saying that we're going to succeed at this goal, but I believe that if we do succeed at this goal, that there isn't anything else. I believe that if we can consistently run things faster across a huge set of architectures and a huge set of different models, I think we have to win.
And make the switching cost low.
And make the switching costs low, but I actually think we're good enough on that front. I think today, if TinyGrad were 30% faster, a lot of people would be switching.
Yeah, the problem is does it look like a uniformly 30% faster, or for something it's faster, something slower? Because many stuff in TinyGrad front end is pretty slow.
Well, so let's compare that to self-driving cars. My theory is that it's mixed at the beginning, and then the end-to-end approach just starts to pull away. So at the beginning, you'll find right now there's some things that are faster in TinyGrad and some things that are faster in Torch. Most things are faster in Torch. Like our gems are just bad.
No, there are a lot of stuff that we just in principle doesn't support, right? Anything
Like what?
that has a for loop, a condition, some fancy CPU stuff.
Yeah, I'm not sure this is a problem. You can always just keep that in whatever other framework you want. That stuff's usually not like, I don't know any neural networks that have that stuff like deeply embedded in it.
Okay, I don't know either.
For loops, yeah. I mean, we can.
That's the thing. That's the thing. Kind of is part of this, right? Because we are. So this is definitely a limit. Say, for example, we probably don't support user insert arbitrary code into as an op or something like that.
I don't think we should support stuff like that. I think that, I mean, there might be a way to like encapsulate user code in such a way that's pretty isolated from the rest of the graph. But of course, that's not going to be fast. But I really don't think this is much. In terms of for loops and conditionals, I mean, we should support for loops. We should support things like RNNs. That's just range on the overworld. When it comes to if statements, well, why do you need an if statement and not a where?
Because where do you compute both?
But that's implementation. It doesn't matter.
Oh,
right?
Why? Isn't that the reason why MP is MP?
What? So you're saying you won't be able to search correctly for the branches of the where?
Yeah.
But no, my point is, I mean, you say that this is a feature we don't support.
That's too much detail.
Well, you say it's a feature we don't support, and where, like, there are some conditionals you actually can't express as a where, and those conditionals we don't support.
Yeah,
but
we don't support data dependent. Anything data dependent? I mean, we can support it. It's just not jittable.
Well, what do you mean by data dependent? All right, like where is data dependent?
No, the depends on say like non-zero or something that requires you to evaluate part of the stuff for your second part. Because it's a shape related stuff.
Oh, I mean dynamic shape, sure. Yeah, we don't support dynamic shapes. Yeah, that's everyone should move away from dynamic shapes.
Yeah, but
true.
Sure.
That is one clear example of something we will never support.
Yeah.
There's a few fast top K that need data dependent branching. Yeah, I think that. But there's definitely ways to write top K that don't need data dependent branching. Like data dependent branching is a really bad idea. Data dependent branching is a branch mispredict and a pipeline stall. That's the stuff that makes code unpredictable. So, no, I don't know. I mean, I'll bet like there's no major neural network that has any data dependent branching stuff.
Yes. Okay. So we want this target neural network to be simple enough, but not too simple, so we have a chance.
Well, we want it to be expressed like Yeah, like in this language of sure, you're right. If the world of neural networks becomes too simple or too complex, we lose in both cases. If it
Great.
becomes too if it becomes too simple that like it's just literally well everyone just uses a transformer or everyone just uses this one trick, then yeah, okay, there's no winning there. That just will be super optimized by things that can explicitly code for it. And then if it's too complex, it just starts to look like code again, and then actually probably like an LLVM MLIR style approach wins.
I guess it also depends on how big your user team is, right? Like people in general saying some of their projects depends on MLIR. I'm pretty sure they probably don't need every piece of MLIR, but the fact that they can pick a subset and just work on a subset maybe works for their approach.
No, but I think that this all just goes away. I actually think that let's see if we can understand my project is based on that ecosystem. The problem with MLIR and things that look like that are like it's really easy to like get a foothold. Like, oh, I'm going to use this. It's kind of like React. Like you just, oh yeah, of course, we're based on MLIR. But I think that like what happens here is like all of the code they write just kind of becomes redundant. Like all the code they not redundant, but like useless. Like
Yeah. But why
let me
is that
think.
a problem?
Oh, well, I mean, it's just why you win. Right? It's just like MLIR might put together a really good guide for how to port to your new accelerator, and you just need to support these 162 ops. Okay. Yeah, okay. I have a team of people. I can assign them all the ops. It's kind of like the approach that like NVIDIA and AMD are taking now.
I mean,
But
isn't that the same for Tinygrad? You support 20, then if you can support 20, why can you support 200?
because our ops, well, I mean, our ops don't really look like their ops, right? Like Conv2D is not an op.
Yeah, but how bad can that be?
Well, the problem is not that just supporting the one op is bad. The problem is not, oh, I'm going to support Conv2D. That's not bad. Okay, but what D type? What about if
Uh,
you're doing weird Conv2Ds where the batch size is really big, but the channels out is one? Right, like, is that
no,
going to affect
I
anything?
mean, our tensor.py is only 2000 lines and it has every piece of that, right?
Well, yeah, no. But our tensor.py is not a. Our tensor.py, Halide really talks about this well. Our tensor.py is not the. Uh, our tensor.py is the spec. It's not the schedule.
Yeah, but I mean, I don't know. Back to your D-type problem, I don't see why you cannot just duplicate and implement everything for your 10 D-types.
Well, okay, but now you're not implementing 200 anymore. You're implementing 2000.
Yeah, but I'm pretty sure I have LLM and it can just copy paste everything for me, and it probably
No, you're gonna start vibe coding these things. How are you gonna check if they're correct?
I just run some tests. Is that hard? Isn't there
who's gonna
compliance
ma-
test
who's
for
who's
this
gonna
200 up?
who's gonna maintain these? Oh, it's 2000 now. You have 10 D types.
I don't know. I feel it's not that difficult. Yeah, I mean, if ultimately the end user only requires 20 of those to work, who cares if the other 1980 are bad?
Well, yeah, sure, right. And if this turns out to be the world that we live in, if the world that we live in, it turns out that all you need to get to work is basically the 10 things we're gonna have to make fast for the AMD contract, then yeah, maybe it doesn't matter. But I don't think this is true. I think that like, okay, so now you
Oh, I
have
mean, it's kind of true, right? The fact that Torch until today still doesn't have uint 16 and uint 32. Like, who cares about those D type?
But no, it's not just about those D types, right? It's about, so if you're like, okay, fine, I'm just going to implement these 10 things and make these 10 things super fast. And then I'll be able to do something like train 405B. Okay, now you want to do it across 10 GPUs.
Okay.
How do you do that? Do you write a sharded form of the kernel? Do you have a separate library you call out into to do the communication? How do you properly overlap that?
You just find your network primitives in Nickel. Use that.
Okay. Okay, so you find your network primitives in Nickel. Okay, that's great. So, what if, like, again, yeah, as long as you're using this exactly the way it's intended.
No, so I guess my point is now there's no doubt people discuss about NVIDIA's mode being CUDA or Nickel or whatever chips they have. I always feel it's a lot more about their users and how they are using neural network or developing neural networks. And I think claiming there's a way to win needs to find a way for these users to have incentive to use any grid other than
Well, I think you just have to. I think you just have to make it faster. I think you just have to make their workflows faster.
Yeah, but the problem is how much faster.
I mean,
And can it be made like much faster?
depends what you're doing.
Yeah.
If you're doing batch size 1 LLMs on a single GPU, no, of course not. But if you're doing any sort of training job, oh yeah, tons faster.
You don't have a really real example of this over a slightly more complicated model, right? So
I mean, like,
every big training models that kind of requires multi-machine or big clusters are the simple one.
yeah, but even, I mean, just as proof that like you can continue to. Okay, again, I guess it depends what you're comparing to, right? If you compare, look at how much more efficient DeepSeek is than the other ones. DeepSeek made it 5x more efficient, and I think there's a lot more to go there too. I think there's even another 5x.
Okay, I don't know.
Well, yeah, I mean, it also like it comes down to being able to like repeatably. It's so difficult to debug any of this. So Comma's still training on BF16, and like sure, we'd like to train with BF8, but you see what happens every time we try to use smaller D types. Like they don't work, and then like why don't they work? Okay, which op is it? Okay, let's go through. Let's stick floats in places. Let's see what fixes it. And then I even think it's worse than that. I think that like some of the kernels are just broken, or like numerically unstable, or once you get down to these small D types.
Yeah, but isn't this an argument for specific D type working? Because we kind of use a lot of rewriting rules that assumes everything's just perfect real numbers.
Yeah.
But it's just not true for a lot of smaller D type, right?
I mean, I think we're gonna start to need like a different approach to some of this stuff.
Yeah.
I think that like the current way that we're doing rewrite rules may not scale. We need to figure out how to leverage more search and optimization. Like if this wins, this is how we win. We win by having something. We win by having a space that's way more amenable to large scale computerized search and optimization than the competition.
Great. So I mean, okay. So now we kind of agree that have a com3D guy is bad, but maybe you need to have a B float guy.
I don't think so.
No?
So here. There's a good
Or
reply
I
to
guess
my
more D type guy.
there's a good reply to my tweet right here. I'd say general compilers have a lot of hand-coded optimizations. Why assume neural network compilers would behave differently? And it's because of the halting problem. It's because there's no way. When you have a neural network kernel, you can benchmark it. And every single time, no matter what data you put into it, it's going to run in the same amount of time. Whereas no normal program behaves like that.
That's I agree in theory, but is that really the bottleneck? Why?
I think so, yeah. I mean, I think it's impossible to reason about code.
Okay. Great. Okay, that was fun discussion. More fun than the following items. Let's move on to other items.
The Apple Llama thing. Yeah, I want to finish it up. I think it's a nice. I mean, it gives people a way to pip install Tinygrad and do something right away.
As it imports extra.
No, it doesn't. It imports nothing.
Okay.
It's 100% pure Tinygrad. It's 150 lines, and I was playing with Olama last night.
Mm-hmm.
It's not good. like I'm still waiting. The I don't know if it's the sampler that's bad, but the models they lose coherence after.
Which model are you using?
I was trying a bunch of the fine tunes. I was doing like role playing stuff, and they lose coherence after a bit. And they just they start repeating over and over and over again. I don't know. It's things you'd never see ChatGPT do. So I don't know if that's Olama or the models or bugs in the implementation or samplers.
Probably model and how big.
These are like 12B models. They're not.
12B is pretty bad. I don't know. Okay.
I don't know.
I mean, that is not something we will fix with our Olama implementation, right? Because it loads the same model, it does the same thing.
Agreed, but the thing about our Olama implementation is you have hope of fixing it. I was looking into Olama trying to figure out how the samplers work, and it's just spaghetti.
Do you also want to look into how Nemo works? Okay, anyway.
How Nemo works? Oh. That's probably even bigger spaghetti than Olama. Olama's it's fine. It's you can read it, but it's not Olama. Sorry, it's Llama CPP.
I think that's generally the problem for maybe MLIR development similar in a sense that it probably has 200 different knobs, and if you are a experienced developer, you can keep those 200. It's like our flags. We probably have 50 of those, and if you are experienced, you can have those kind of know what you are doing. But if you are not, then the bigger the flag look like, the harder for you to realize what's being.
I was asking ChatGPT for sampler parameters. I was copying and pasting them. I couldn't tell which ones are really better. We're not gonna fix that, but at least we can write something that's very, very simple and then repeatable, which I feel like a lot of these things kind of aren't. I think that a lot of these LLM implementations are just broken, but there's no simple way to benchmark them and see that. They're getting 20 points lower on these things, on these truthful QA than they should. But yeah, I don't know. I think it'll be nice to just have, even if it's just the same, it'll be nice to have Python-M tinygrad.app.llm.
I think it's also a good if you write a clean and easy to adopt one, I think maybe people would be interested to write other app in that style.
I mean, the only other app we were really thinking about is an image app, and it's got to be so simple. Like, it's got to be, if we could do an image app also in 150 lines.
Okay. Okay. Sounds good. Do you block on any of other refactors for your thing?
Oh, wait, we did get boxes?
Yeah.
Oh,
Oh, it's delivered. Great.
it's delivered. There was just a typo in the tracking number. Awesome.
Okay, new box. Great. Any other? Are you blocked on any of the refactors for your thing?
Not really. They're
Merge
just
GQA.
what?
I merged
Emergency QA? Oh, nice. You mean for the app or for just in
No,
general?
for the core refactor, the many things we want to refactor.
Yeah. No, I'm not really blocked on anything. I'm just trying to figure out the right order to go about it still.
Okay.
I think the first thing is just to we made a mistake when we call simplify ones at every optimization step, and we shouldn't do that. Because that changes the meaning of like upcast axis 2 if you do upcast axis 1 beforehand and axis 1 disappears.
Yeah, that logic is also before my time, so I know very little about it.
It's bad. It wasn't well thought out. If we fix that, there's a path
If
to
you only do that at the end of the up stuff, is it worse?
I don't think
You
so. No,
start-
I think
you start from there?
that changing that is the first step, and then you can apply the opt-ops in parallel. Right now, the opt-ops are inherently a serial process. There's always going to be some serialization on the same axis, but like there's just no way right now to like it's just such a poorly specified space. We clean up the space, and then also opt-ops should be able to apply to. Right now, all opt-ops basically apply to the sink. This is wrong. You want ops like unroll to apply to the reduce, not to the sink. So then you can individually unroll the different reduces.
How about reshape?
What do you mean
So
reshape?
reshape merge two together and redistribute.
Well, so your views all need to be pushed to the outside.
But there are limits for, say, if your number is too big for the hardware, like you can specify for each global, for example.
What do you mean?
So if you're in, so there are something in the lower that shape and split one dimension to multiple because of hardware limitation.
Oh, I already separated that. That stuff's already separated out. The
Oh,
the
okay.
mapping of the ranges to GPU should be like the last thing we do. I already separated that out. You could
No,
totally.
but what if you need to do more things like really change the compute layer?
I don't understand what you'd have to change.
Split one global into two.
For what? For the GPU
Because,
thing?
yeah, for the GPU because the size is.
Yeah. If you're just doing that for the GPU, you can do that at literally the last minute. You don't need to do that in the kernel.py. That's already all removed. I moved all that to later.
Okay.
So if you have like a range that's too big and can't fit in your global dimension, and you want to split it across two global dimensions, like when you remap the ranges to specials, you can just map them however you want. It doesn't matter, and then run sim again, and it'll clean up whatever things there are.
Okay.
But this is already dealt with. The GPU thing should be dealt with at a completely different layer of abstraction than the ranges.
Okay, so Okay, sounds good. Okay, moving on. ML perf llama. I will make something that turns 8B model this week. I was still reading all the dataset stuff.
Sweet.
I would try to install Nemo and see if I can just use that for dataset. Or at least I have a way to know my implementation is correct. So what happened is Google tried to submit for Llama 405B, but they removed their permission. And I think partly is because they didn't upload any of the implementation details for how do they get the sequence to become individual training examples. That was annoying for me because I don't have a reference, and they also don't have a reference, and I suspect that maybe they realized that's why they got different converges.
So we have to find it in the NVIDIA code.
So it's more of I also want to get something to run, so at least we can start to improve the runtime. I'm pretty sure the how we pad or mask the token has very little impact on the kernel speed. So I also want to get that working.
Yeah, agreed.
But yeah, for us to, I think, faithfully do this benchmark, we want to match how this down to gather data. So if I can find a way to import Nemo and also gather data, that can also work. That's my thinking. Because
Cool.
there are apparently many weird strategies they use when they generate that data. So I think some of it is disabled. I don't know if all of it is disabled, but if it really goes into implementation details in how they pack sequence into one, I don't really see us replicating everything correctly.
Yeah, I mean, I don't know. Almost what I would do is just kind of hack the Nemo stuff to just how big is the data set?
A few terabytes. I think everything all in all fits into memory.
Fits into memory? You can't fit a few terabytes into memory.
It's like two terabytes something.
Yeah, but no, you're not gonna put that in memory, are you?
No,
I
if,
guess-
if your data sampling really is pick a random place and read it, then you really want everything to be in memory. That's why I downloaded.
No, but there's no way I'm loading 2 terabytes into memory.
You can also shuffle on disk.
Yeah,
No,
or
but,
I mean,
there are 10 files on the disk.
I mean, you could shuffle on disk and then just read sequentially.
I also have a million IOPS.
Yeah.
No, you cannot shuffle. You cannot shuffle that and read sequentially, right? Because then you already decompress your data set to be 8,000 times bigger.
Wait, but I don't even understand. These drives have like a million IOPS. How many samples am I using per second?
8,000?
Yeah, what does I need 8,000 samples per second? Any SSD can do that. Any SSD can handle 8,000 reads per second.
Okay, I don't know. Maybe that's fine.
Yeah, no, I'm sure we gotta just figure out how to leave it on disk and how to just pull the things off disk that we want. I don't think 8,000 should be a problem. If it was 800,000, okay, that's more of a problem. Then maybe we have to think about RAM. But
Yeah, we're trying SAS one, so that's probably fine.
cool. I mean, yeah, we're doing so much processing on each one of these data things. I can't imagine this being a...
Okay. Anyway, that's my main goal. Let's move on to this. If you are saying stuff, I cannot hear you.
Can you hear me now?
Hello. Yes.
Great. I merged the tiny device. You can see it in the timeline. It's on the top. Shows the Python time. And this week, I think I'm gonna merge some ways to like track buffers. So there's a good paper on this where it actually like goes into details about how memory is scattered between like activations and model state and stuff. So I'm gonna try to figure out a way to visualize that for Llama. Like you see a lot of these.
The tiny device looks great. Sorry, go ahead.
Yeah. So for Llama memory viz, right now we see that the optimizer states just stay alive, like for like 40% of the time, and that's not really much of a useful graph, to be honest. Like it's the exact graph that we talked about of like these steps and stuff. But I'm thinking of a different way to view this because I think it will be inevitable that you have like a baseline of your model state and your optimizer, and everything else is just how you can optimize your intermediate usage.
So I would really avoid, in the spirit of end to end, I would really avoid like labeling weights as a certain kind of type. I would ask instead what, like, almost like physics-based characteristics do these weights have? So there's definitely a clear distinction between short-lived weights and long-lived weights. So there's weights that only there's buffers that only live during the execution of the graph, and there's buffers that persist beyond the ends. See what I mean by that?
Multiple schedules, yeah, multiple steps.
So
Yes.
it's like for your model weight or for your optimizer state, those persist across each training steps, for example. But gradients is not. Gradient, you can all the gradients of this steps can disappear at the end of this step, and if needed, they can like be like create a new buffer for the next one. Similar to activation.
Yeah, I think that's a good distinction. I mean, I think it's that same distinction. Like, however we decide this, we want it to be the same way the memory planner decides it too. I'm also, so I see here in the tiny device, I'm seeing like get program for E3. Could we actually see the rewrites?
Click on it.
No, that's not what I'm saying. I'm saying like in the timeline, it's just a big thing called get program. But that's going to be a whole lot of different rewrites, right?
Yeah, you want to see the rewrite steps.
Yeah. I mean, it'd be cool if it was like a hierarchical, like you have like get program at the top, and then like, okay, here are the 10 rewrites that went into the program, and then when you click on the rewrite, it actually jumps to that rewrite in the thing. But it's really good already how I can click and it goes to the thing. This is a place where Tinygrad is way ahead of everybody. Like, imagine seeing this for LLVM.
Observability. Yeah.
But yeah, so I'd like to see underneath these get programs, I'd like to see it showing me all the different rewrites that happen. Because I see like a get program taking 647 milliseconds. Is it really?
Pretty sure.
That's crazy. I wonder what rewrites are taking so long. You know, this is very exciting. Yeah. Add the rewrites and then yeah, so I missed what you were saying about the you've a paper that was talking about like what the different types of parameters were?
Yeah. So right now we have the buffer graph, but there's not actually any label of like what this buffer actually is. or how it's used. So
How might you get that label?
I trace it back to the kernel and I get the kernel metadata.
Cool. Yeah, that seems nice. The whole handling of metadata right now is a little bit janky. Like a better handling of metadata that can show, like, almost like the line that triggered. Okay, where's the line that triggered this compute? Where's the line that triggered this buffer creation? Any of that stuff that we can trace back is great.
Trace it back to the realize.
I mean, even better than the realize, right? I guess there's both, right? There's where the specification happens and then where the compute happens.
Yeah, you can imagine like one leads to the other. You can walk the trace back.
Yeah. But I mean, I think you're making good progress here. I really like the tiny device. So yeah, I mean, play with it and just make sure whatever it is stays performant. My theory about the main reason people don't use profilers is that they're not performant, is that they have way too much overhead. If there's a profiler that's basically free, and they're too hard to run. But if you have a profiler that's basically free and runs with a single environment variable, that's great. But yeah, okay, so you want to be able to click these buffers and see what kernels use them.
And like that's one possible direction. Another possible direction is like the cache information, like the physical information about like how.
Oh, like what the actual like physical address of the buffer is?
I mean, like so I saw these tools from AMD that they have. It's pretty janky, but it works. I think like it shows you about when you have a memory allocation. Did it hit the L1? Did it how many times did it hit the L2, etc.
Ooh, yeah. I mean, yeah. If we could start to, there's been a bunch of those posted in the channel. The ones that like show the NVIDIA has a profiler for this too, that show you like the usage of each bus. Yeah, I mean the main problem with using those things is they're super hard to run and they kill performance. But I don't think that's inherent to the things. I think it's just bad implementation.
Cool. Looks nice.
Progress in this channel.
Sounds good.
Moving on to drivers.
Yeah, so been working on the NV PCI. So now we have huge pages and performance is so sometimes it's better than the NV, sometimes it's worse. So yeah, so I mean it's better in most of cases when it's run on the single device. Sometimes I mean the numbers say bit worse because of the in-queue time. So I'll check this. So general the GPU speed seems to be good.
Great. Do we have 5090
yeah,
support?
not yet. So yeah, so the next step I've been doing several cleanups for 3090. So yeah, so actually this week I'm going to, so the primary goal is just to train some BERT and maybe some other networks to just make sure it's stable for a week or so and merge it in CI. And yeah, in 5090.
Cool. So I see this change here to the to system.py and you use NVPCI. So this is for large pages? Will you do this? I see you doing this like 2 shift left 20 if size is greater than 8 shift left 20.
Sorry, what
Sorry, I'll link
request
it.
is it?
The
Enable pages.
NVPCI one.
Let me see. Oh, this one. No, actually, I've already merged this. We had it. So this part I merged it. I mean, we had it for NV as well. So basically, that helps. So basically, the difference in hardware between AMD and NV is that AMD can fit different, like in TLB, they can have different sizes, like which has a power of 2, like 4K, 16K, 8K, and so on. So AMD support only, NV support only like the page size in the TLB, like 4K, 64K, 2 megabytes, and so on. So because of that, yeah, we just need to align the size, because the tail of the allocation could be a lot of small pages, like 4K pages. And because of that, we just overline the size to allocate it as one huge page, like the tail of the
That makes
allocation.
sense. So AMD's, how can you have a TLB that doesn't match the page size?
Yeah.
But how? I mean, how does it like? What if it sees like contiguous pages? It like merges them or something?
No, there is a flag in the page table.
Oh, that says like these 4 are one TLB entry.
Yeah.
Yeah. Interesting. I've never seen that before. But cool. Yeah, seems like good progress. Excited to have 5090 support. And then what we should do is we should add 2 of the H machines to CI. I think maybe instead of removing it from the, well, I don't know. It's up to you if you want to remove from the green boxes, but I think adding 2 of the H machines and always having neither of the drivers inserted on them is a good idea. They do have 5090s though. But yeah, then we can test like the 5090 driver and test the 9070 XT driver.
Mm-hmm.
Can we DMA from an AMD card to an NVIDIA card?
Yeah, I think we can.
Right, that'd be cool. I think that's
Sorry, go ahead.
I think that'd be a great thing to test in our CI, right? I think that like you want to get to stuff that like no other driver would dream of doing. It's that we are going to be able to DMA directly from NVIDIA to AMD.
Who is doing that? Other than
We
it's
are.
cool. Okay.
Yeah, I mean, but no, it's not just that it's cool. It's also like it shows that there's a framework. I mean, I want to start using the same framework for NVMe drives, the same framework for network cards, that we can actually DMA across these heterogeneous devices and not have to use something called NV Direct or whatever it is.
Great. Imogen, you said it's faster for single device, single GPU. What about multi?
So it's also fast. I've tested ResNet from the CI,
okay.
which is not beamed. It's also like few percent faster there. But yeah, it's a bit slower, like running Llama, and actually, like the GPU times are the same or faster, but the NQ time is a bit higher. So yeah, that's to investigate.
So what I want to get to for this is I want to start moving the implementation of our drivers into Tinygrad. Like it should be a CPU Tinygrad kernel to do all the updates and not Python code anymore. We started doing it. You did this with like the how we do the symbolic stuff. But yeah, the eventual dream is that these HCQ drivers themselves become written in Tinygrad. And whatever stuff's going to require to do that. But like, imagine also being able to run them on a GPU. Or imagine being able to have just a Tinygrad kernel that does the NQ. So like GPU 2 can NQ a kernel on GPU 1, or maybe even on itself.
Yeah.
But yeah, that should fix all the NQ times, I think, too. Like it's just some like compiled C code to.
Anything else for the driver?
No.
Moving on to cloud.
Still file system progress. Better. I'm hoping to have something deployed this week. And start hitting it. See how it performs. There's some. I think my main issue right now is there's a separation between chunk queuing, like hashing a chunk and then storing it. Because I think currently we assume that all machines that run compute have drives.
I don't think we have to.
Yeah, because then we have the issue of okay, are we sending the chunk twice then?
Oh, you're saying like what happens if we hash it in a different place from the drive?
Yeah.
I would guess that the machine that does the hashing is also the one that does the store.
Yeah.
Which is, yeah, I'm okay with that. I'm okay with assuming that all machines that have drives have compute.
Okay.
Yeah.
Okay.
That's totally fine. We can assume that stuff, and then also we should think about how to run a local version of this file system. Like I want to switch cache downloads over to a local version of.
We can have locally we can have the same block storage format. Like it can be hashed in the same tree. I think that's good enough.
Yeah, I think that's all we care about.
Yeah.
I think we don't even. I guess we don't even really care about like how the files are stored, but it's some.
Yeah. As long as it's the same tree, and then you can hit the same hashes from the cloud or from locally, it's okay.
Yep.
Yeah.
And like, yeah, ideally it should all just be like. It should be like a read through cache. Like it should be like a. Like. The only way to access things in Tinygrad's download should be by the hash.
Okay. How do we download something into, like, if a user wants to run some new llama model,
Well,
I
I'm
have to pre-download it.
No, I'm saying like sure, you can keep around the helper methods, right? You can keep around fetch, you can keep around from URL, but under the hood, what that should do is not stick it in cache downloads. It should stick it in the local Tinygrad file system.
But then, how will the user specify that they want? Like from URL is you providing a URL.
Yeah.
Then do they also provide the hash?
We can store that in the SQLite if you want, or store that in something.
Okay.
Yeah, we can store a lookup in something. I guess if we lose that lookup, they'd have to re-download everything. It kind of sucks.
So everything would re-download and then everything would recompute.
Yeah, my only like point with this is that I want to make sure that if they do a from URL, however that works in the back end, if they then do a from hash on the same thing, it also works.
Yeah.
Yeah. That's the like exposed requirement to this.
Okay.
From hash and from URL should use the same backing store.
Yeah. You could also just hash the file and then store the hash to file lookup.
Oh, like as a file? Yeah, that works too. Yeah, maybe that's the way to do it. Just like keep the download directories, just be kind of like instead of the file containing the data, it contains the hash.
Okay. Anything else?
Yeah, just whatever you just wrote.
Oh, this is great. 10% overhead, well within the bounty target. Awesome.
Hard to know what devices are on what hosts in URL.
What devices are on what hosts?
Yeah. I think just currently our device specification isn't quite getting a group ID to OMS device. group ID.
Yeah, I mean, there's no reason that ops device is kind of this. Yeah, the colon thing is kind of bad.
Yeah, we kind of need a better way to specify more complicated topology.
Yeah. I'm
kind of don't have that right now.
totally okay. I mean, maybe the first thing to do is to have ops device have that number after the colon be a const input. And then you can have multiple, right? Like its sources can be like as many consts as you want, and that's just a topology.
Okay.
Like I'd be fine with that. And so instead of having like an explicit thing called group to, you can just have like, yeah, the first refactor would be getting rid of the colon, and then having that be a constant. And then there's no reason that you can't support 3 constants if you want a 3D topology. I don't know, but you also want to have the idea of like a max.
Mm-hmm.
Like I don't know if device should include the world size.
Yeah.
Maybe should. Oh. Some kind of refactor there.
Moving on to Onyx. A deep complaint because Onyx is still not in Tinycorp proper.
Yeah, let's do it. Let's move it in.
So. Oh yeah, there was a change Onyx runner to take file as an input, and like got quantum benchmark really slow, more than 100% slow. So it was block on that. Can you speak more about what else is needed to move Onyx to Tinygraph proper? Other than line count?
You mean me? I don't know.
No, I'm asking.
Oh, zero cap, yeah.
Okay. Maybe not for this meeting, but I'd like to know like what, because we fixed a bunch of stuff already, right? So I want to see like other than line count and maybe some cleanup for general styles and functions. I like to see like what other blockers are there, so that we can have some estimation for if we want to make this happen faster. Is there a way? Okay. Some symbolic stuff for us Lycos.
Hi, can you hear me?
Yes.
Yeah, so I updated the PR that George merged this week and then reverted. And it is now also producing the right output. Basically what happened is I fixed one bug and then there was another bug that was just silent. So after fixing the first error, it just silently produced like the wrong output, which, yeah. It's
Cool.
fixed now. Like,
If I merge 1188, this is fixed and has a test.
yeah, I mean, I was just using like Squadron made a unit test from because I couldn't run the actual LLM app, so I just used the unit test, and the unit test is fixed.
Why couldn't you run the LLM app?
I don't know, just used a lot of memory.
Oh, that doesn't sound good. All right. But yeah, no, unrelated. Cool.
Wait, is it not only a 1B model?
It's a 1B model, but it does use a lot of memory.
Oh.
Oh, it might be the context size being crazy big too.
Oh.
I don't know, but cool, great. I'll merge this. Looks good.
But yeah, I think it might be more like I also noticed that seal div is incorrect for UOPS. Like it's only the helper, like seal div helper, is only correct for int and not for like symbolic. So I think if stride is not, I don't know, and it might produce problems.
I mean, what we really want, and I think what a lot of your project is going to be like just thinking about all these cases and just fixing them. Like, we need to support arbitrary symbolic. What I want to do for the LLM app is I want the T, like the number of tokens, I want that to also be a variable.
Yeah. Yeah,
And
because I don't think there's not a like there's a fuzzer for the shape tracker, but I don't think it works with variables.
yeah, I don't think it does. I don't think it does at all. I mean, in theory, what we should be able to do is just like anything should be able to become a variable, and it should still work.
Yeah, yeah, yeah.
So yeah, I mean that's kind of the test. It's kind of the direction to go here.
Okay. Anything else?
Yeah, going like working more on the new fuzzer, and like now I'm using the bit vector fuzzer, which also tests sort of overflow behavior. And like there's some current there's some, for example, if you have an inequality like a less than comparison, right now that might just get folded to a true or false. Whereas if one of the sides of your comparison can overflow, then it's not actually a constant.
Yeah. So
Yeah,
I see. Sorry, go ahead.
I think overflowing is just implementation details. It's like having the number overflow. It's pretty much always not an intended behavior. Unless I don't know if people are doing crazy stuff for uint. Maybe people use the wraparound for uint for other stuff. But for signed integers, for floats, I can't imagine. Like float doesn't have this problem, so maybe just int. I don't think people use this as a intended behavior. Maybe that's fine. Because when we start to consider like overflow in these min max and more math formula stuff, that's a lot of your implementation details of those D types.
I mean, what we might want to do for this, and we used to have something like this, is we just might want shapes to not be int32s. We might want them to be like arbitrary integers. I think we used to have something for this, but it was taken out because it was slow. But they should just be like arbitrary precision integers, and then there can be a pass later on which puts them in a real D type.
I guess my problem is that the fuzzers was going over each rule in symbolic one by one, generating random UOPs, and some of the UOPs are not equal before and after the simplified because there's some overflow.
Yeah.
Yeah.
So I think for the actual ALU, we have a pass that change the D type for the number from int32 to int64 if it surpassed that. We still have it? I think we still have it.
Yeah, yeah, but I mean that's only for like integers in like
Yeah, so I think
shape.
that's the kind of the intended behavior, right? So if you say the fuzzers find the numbers that intermediate or outputs overflows, the actual intended behavior is to change the type so that it doesn't overflow. It's not like we want to make the overflow behavior the same.
Yeah. Okay. Okay, I'll move on with that then.
Yeah, because otherwise we
Yeah,
start
the test cases use overflows. Yeah.
Yeah, we really don't want in the the math rewriting rule start to consider, okay, what if this overflow?
it's already annoying to have none and 0 and if.
Well, yeah, then what we might want to be using is, again, this like arbitrary precision D type, and it's almost a question if we only want the symbolic rules to apply to this arbitrary precision D type, and we can do all the shapes and the indexing in it.
Mm. I mean, there's not like that. I mean, it's only the rules with like comparison operators that are causing problems. Most of them are fine, I think. So
Yeah, I think my fundamental thinking would be if it's something that has an intended use case that user will want to happen, then we track those. If it's just the way we run fuzzer or benchmark and it's like really trivial, then don't change the core properties of D types or something because of that.
yeah. Okay. Yeah.
Cool. Let's quickly go through other bounties. Let's see, Flata, you have anything to add for RetinaNet?
Yeah, so I finished the rewrite. I did find it slower for now, so I'm trying to debug where that is, but I kind of want to do the correctness check. So I'll probably just run the eval script and make sure that the accuracy or the score rather matches with the existing one. I still have to root
How
causation.
can that be slower than the already very slow one?
There is, I think, like 2 for loops right now in the current implementation on NumPy. I don't know. I started commenting out code just to see like where the slowdowns are.
Okay.
I JITted it as well. I think only the main post process. So I think the other ones I still have to modify it so that it can be jittable because it needs to use the variable as well. It needs to be a variable number for some of them as well.
Interesting. Okay.
Yeah, I'll provide more a better write up once I understand where the slowdowns exactly are in this case.
Cool. I think these experience are very important for Tinygrad development because it certainly links to how easy other people can rewrite existing stuff in Tinygrad. So anything you find, if you can like write, even just for the things you encounter that you find any inconvenience or anything you think the framework is not doing great for your development, that would be good to know.
Okay, sounds good.
Cool. We have a bounty that removes all the realized int set item.
Wait, did someone submit for that?
No.
Oh, yeah, I mean, that'd be a great one. I also really want to remove that realize in the KV cache, too. I think now we have a really good understanding of what a sign is, though, which is exciting. Like, we used to just have a sign, and it was this, like, nightmare, and no one really knew what it was. But, like, it's just store. Reasonable.
For your test, how do you envision the final single kernel look like?
Which test?
So you write a range of size 10, and you say for I equals to in range 10, the i's element is assigned to I.
Yeah.
How do you think that single final kernel will look like?
Oh, hang on. Let me look at what I wrote again. I vaguely remember writing the test set item loop. I just imagine it being literally just that. Literally just 10 stores.
And each to the element?
Yeah.
It writes a
Like-
for loop?
It's not a for loop. No. The kernel obviously won't have a for loop in it. The kernel is just going to have 10 stores in it. See what I mean?
Yes.
Like it's just going to have, okay, so it passes in some buffer. And the buffer has like buff sub 0 equals 0, buff sub 1 equals 1, buff sub 2 equals 2. It's not going to like extract the for loop or anything.
Yeah, but how do we write kernels like that now? And we have a single kernel that stores to different parts of.
It's not done correctly now. I know how to do it. It's the problem. Yeah.
So because for now we only support kind of two types, right? One is store everything inside that buffer,
Yeah, we don't.
or take a slice of that in the outer world and kind of store into that slice.
Yeah, this is both the wrong way to do it. So you don't need to do it in the outer world. You can do it in the inner world, and like what the inner world will be is that kernel will basically become a lot of like load store, load store, load store, load store, all put in one kernel, and then it'll realize that the load stores are irrelevant in all places except I, and it'll just get simplified down. We already do have logic for this. We already do have logic where if you're doing a load store and they're in the same place, then it just avoids it. It just doesn't do it.
I see. Cool. Okay. Other bounties, the refactor ones, I didn't see anything that's ready for review other than, do you want to try the CFAR with Torch?
Oh yeah, sorry. I was gonna try that last week. Okay. I'll do that this week. I did the other one though.
Yeah, I saw. Cool. Okay, I think that's it for this meeting. Went slightly over time because we were discussing other stuff.
Cool.
We have Torque Boy.
Comments coming to the meeting now.
Great. Okay, that's it. Thanks everyone. See you next week.
Bye.